Hey everyone, and welcome to today's explainer. If you are a first-year chemistry student, you are in exactly the right place. Today, we are going to unpack a pretty fascinating piece of microscopic drama that takes place right inside your beaker. We're talking about the Fittig reaction. If you've ever wondered how chemists literally force two stable, ring-shaped molecules to hold hands and bind together, well, we're going to track the exact movement of electrons that makes this chemical marriage actually happen. And real quick, before we jump into the mechanisms, I want to mention that this foundational breakdown is brought to you by SHREE-EDU-SPARK. They're an awesome organization dedicated to igniting minds and shaping futures. And they provided the source material we'll be diving into today. Okay, let's dive into this. Here is a quick look at our roadmap for today. Number 1, meet the Fittig reaction. Number 2, the ionic pathway story. Number 3, the radical pathway story. Number 4, pathway comparison summary. Number 5, crucial lab conditions. And finally, number 6, Fittig versus Wurtz-Fittig. Let's start with part 1, meet the Fittig reaction. The destination, biaryl compounds. You know, whenever we look at an organic mechanism, it really helps to start with the ultimate destination. For us, that's synthesizing biaryl compounds, basically getting two stable aromatic rings directly joined together. So looking at the fundamental equation, we start with two molecules of an aryl halide, that's the Rx, and they're reacting with two atoms of sodium metal. The sodium steps in, completely strips away the halogens to form sodium halide, and leaves us with our grand prize, the coupled RR biaryl compound. But how does this actually happen on a microscopic level? Well, that brings us to our electron protagonist. Moving right along to part 2, the ionic pathway story, which is also known as the organometallic route. So in organic chemistry, this route is pretty much considered the dominant macroscopic story. In step 1, the sodium atoms act as eager donors. They transfer their electron sparks straight to the aryl halide. This forms an aryl sodium salt, which is an R- carbanion and an Na+ cation. Now think of step 2 like a highly targeted magnetic strike. That newly formed aryl carbanion is a super powerful nucleophile. It actively seeks out a second aryl halide, attacks the carbon, and forcefully displaces the halide ion to couple the two rings together. But chemistry is never just a one-lane highway, right? So let's look at part 3, the radical pathway story, or the free radical route. In this alternate pathway, the sodium transfers just a single electron spark. This causes what we call homolytic cleavage. Basically, the carbon-halogen bond breaks perfectly evenly, which generates a highly unstable aryl radical and a sodium halide molecule. Because these radicals are so incredibly reactive, step 2 is just pure chaos. It's literally like high-speed bumper cars. Two aryl radicals violently collide in the solution, they pair up their lone electrons, and boom, they form our stable biaryl product.
Okay, part 4, a quick pathway comparison summary. Ionic versus radical, side by side.
Let's put these two distinct microscopic journeys right next to each other. The absolutely fundamental difference here comes down to the electrons. The ionic path relies on a 2-electron transfer to create a charged organosodium intermediate, which then executes a very targeted nucleophilic attack. On the flip side, the radical path relies on a single electron transfer that creates a neutral but super unstable aryl radical, which then links up through a violent dimerization collision. Which brings us to part 5. Crucial lab conditions. Think of this as the essential weather for our chemical journey. Here is your absolute must-follow lab success checklist. First, you absolutely must use a dry ether solvent medium. Second, ensure zero moisture or alcohol is present, like none at all. And third, you need to optimize your starting materials. Note the reactivity order here. Iodides are the most reactive, followed by bromides and then chlorides. Why is that? Well, it's because the carbon-iodine bond is the weakest and the longest, which makes it the easiest one to break when those sodium electrons come sparking in. Now listen up, because we need to talk about the single most common student mistake: using wet ether. If there's even a tiny drop of water present, the highly reactive sodium metal is going to violently react with the water instead of your aryl halide, and it gets worse. Any aryl sodium intermediate that actually does manage to form, it'll be instantly protonated by the moisture. So instead of two rings coupling into your awesome biphenyl destination, you're just going to end up with a simple, boring benzene ring. Moisture literally derails the entire journey. Finally, let's look at part 6, Fittig versus Wurtz-Fittig. Similar microscopic journeys. The source material poses a really interesting question here, and it's a perfect pivot point for us. It asks, Would you like to explore how the mechanism changes when we mix an alkyl halide with an aryl halide? Because remember, up until right now, we've only been mixing an arrow with another arrow. So the crucial takeaway is that you really have to understand your starting ingredients. The purifittic reaction is strictly an aryl plus aryl coupling, and that creates biaryl compounds. But if you introduce an alkyl halide into the mix, you are suddenly performing the Wurtz-Fittig variation. This mechanism couples an alkyl group to an aryl group, synthesizing entirely different molecules called alkylbenzenes. It's kind of like a giant puzzle. By simply swapping out the starting pieces, you change the final picture entirely, even while using the exact same fundamental chemistry. We've seen today exactly how electrons jump, how molecules crash together, and how beautiful new structures are built, all under the strict watchful protection of our solvent. Which leaves me with a thought I really want you to carry into your next lab session. If dry ether is the essential shield that allows the Fittig reaction to even happen, what other organic mechanisms